Oh, let me check. It should be up. If it's not up, I'm going to make sure it's up on Canvas. Resume the recording. All right. So today we'll continue on from the topic that we cover on Tuesday, right? On Tuesday, we start to dive into, okay, I have a program I want to run. How do I design a ship to, first of all, understand this program and give the right control signal to run my program, right? And we kind of like pause at uh, the speed discussion in a sense, right? We are talking about the first of all single cycle architecture, and then we follow on with the multi-cycle architecture, right? Multi-cycle architecture basically means that we're gonna clock our CPU in the way that the long instruction would take more cycles, the short instruction would take fewer cycles, right? And this is good, but is it good enough, right? So in the multi-cycle architecture, when you fetch the instruction, everything else is idle, right? I'm going to the memory, get my instruction. At that point, are there anything done to the ALU, to the register, to the decoder? No, right? I'm basically leave it alone, not using it. What does it mean? It means that I have a hardware that I underutilize. So would it be better if while I'm fetching, the other components are busy running something else, right? And we cover how we can do that today, right? While you're decoding the instruction, we are not fetching anything. I'm just trying to figure out, okay, the instruction we just fetch, what is this instruction? The ALU is not doing anything. Basically, decoder is basically trying to tell what is this instruction and what am I supposed to do? Where's the operand? Do I need to get it from a register file, right? While I execute the instruction in the ALU, I'm not doing anything to the main memory, right? The decoder is also not doing anything. The fetch unit is not doing anything, so on and so forth, right? So what if we can keep pumping different instruction into this idle part? What I'm saying is, let's say I do this. Let's say the ALU is processing instruction 1. And I have instruction, so basically this is my instruction. Instruction 1, instruction 2, instruction 3. So the decoder is not doing anything, right? To make sure I still run the program from the first line to the second line to the third line, what instruction can be run on the decoder right now? So instruction 1 is in the ALU, right? Before we go to the ALU, we go to the decoder. So what instruction can go to the decoder? We have instruction 2 and 3, right? So both of them can go to the decoder. To make sure we still have ordering of like instruction 1, then 2, then 3, I can put instruction 2 in the decoder, right? At the same time, we're not fetching anything, right? So can we try to fetch instruction 3 right now? Yes, right? Because we finished, we finished fetching instruction 2. We finished fetching instruction 1. The fetcher, basically I'll call the fetch unit a fetcher. The fetcher was like, I'm not doing anything. So give me the next instruction, right? I can literally over here, I can try to fetch instruction 3, right? So you think about it this way, you can kind of process these series of instructions while at the same time, each component is doing something useful, right? And every single component, hopefully, is busy doing something, right? So basically, that's the concept of pipelining. So I'm going to use a real world example, right? So let's say I need to do laundry. which is something I hate to do. Like, it's something that I have to do a few times a week to make sure I can repeatedly wear the same polo shirt that you've seen since years ago over and over and over again because I don't have unlimited amount of shirt, right? So I need to do laundry. I have a washer, I have a dryer. And at the end of the laundry process, I mean, sometimes I don't do this. Don't, well, guys, I know it sucks, but I mean, sometimes I don't fold my shirt, but let's be nice, right? I'm gonna fold my shirt. So there are three steps. First step, put my clothes in the laundry. Second step, I'm gonna dry it. Third step is, well, once you dry, you need to fold it and put it in the correct places, right? In my wardrobe, right? So let's say I haven't done laundry in a long time, which is also not a good thing to do, right? So let's say I have 5 batches of laundry that I have to do. This happened a lot when I was doing a PhD. Also, it's something I don't recommend you to do. Like, do 5 batches of laundry is a lot. I'm not saying I don't recommend you do a PhD. It can be awesome. It can be sucky, depending on when and where you're talking. But anyway, so let's say I have 5 batches of clothes, right? You have one washing machine, one dryer. What do you do? So what would be your step? So let's first assume these things, right? Let's assume your washing machine take 30 minutes. And typically dryer will take longer, right? It will take on 1 hour, right? And somehow magically I can move clothes from one place to another, take no time. And folding clothes also take 30 minutes. So what can I do here? I have 5 batches of clothes that I have to do for the whole like laundering process, like going through the washer, dryer, and folding. What do I do? What's the first step? Hopefully you don't put things in a dryer and then washer, right? Obviously, or folding and then wash it. So the first thing is you get the first batch, throw everything in the washing machine, right? So, oops, sorry. So basically, first batch, you wash, right? You dry and you fold. Once you're done, what do you do? Repeat the same process over, right? So how can I optimize this process? What would be the thing that makes sense? That would make sense. Now we're going to the concept of pipelining. If you want to make it all faster, you don't want to wash, dry, fold, and then wait for everything to be over, wash, dry, fold, wait for everything to be over, wash, dry, fold. How can you make it faster? So I'm gonna put it here, batch 1. Exactly, right? Okay, I'm fighting with PowerPoint. Hey. I'll just say B4 and B5, all right? Because somehow I cannot write the word bash. I wash, right? Oops, my batch here. I wash the clothes. Once I'm done with batch number 1, I put them in the dryer. During this time, I'm not using a washing machine, right? So what would be making sense is I wash it here. Then I dry it. While I'm drying, I'm gonna fold the first batch. And I'm gonna wash the third batch, right? Dry it here, fold, wash, dry, fold, wash, dry, fold, right? So over here, let me ask you the second question here. What dictates the speed of this whole process? Which one is the slowest? The dryer, right? Because washing takes 30 minutes, drying takes 1 hour, folding takes 30 minutes. So in total, every single batch, you're gonna be bottlenecked by the dryer, right? So the second question, which is a little bit out of the scope, but I want to put it there anyway. So if I want to improve this process even further, what should I do? Let's assume I have some money to buy something. What should I do? You buy the dryer, right? So that when you finish the second batch washing, you can put that in the second dryer. So you invest in the second dryer. How can you say that that's something you should invest on? True. Okay. That's a great answer too, right? So the first answer is, well, you can get a second dryer. The second answer is to get the clothes that dry faster. What do they mean? That's a great answer because if you think about clothes that dry faster, what does it really mean in a computer? I have instruction that somehow dry faster. What does that instruction do? It means I'm changing the instruction, right? I'm changing the instruction so that it takes less time. I can change from a multiply to an add, for example, an add to an XOR, right? I change it so that it takes lower amount of time. All right, so with me so far? Basically, you can change instructions that are coming in. You can change the unit that have to be processing by adding more of those, right? So let's go back to our cartoonish example from Tuesday, right? We have a kind of functioning computer here. Everything is not being put in the logic gates. Everything is a box, and they are supposed to do the tasks they are designed for. I'm not gonna go into way too much detail on how to design each of these boxes. All right. Just make sure you see lines and arrow. It means that data go from this place to that place based on the arrow, the direction of the arrow. Each of the box has its own task. They're supposed to do certain things, and there are boxes that select each of the signal going into the output. So because I basically explained the analogy of pipelining, right? Can we do it here? The answer is yes. There's a certain reason why I draw the figure this way, because the first thing you do when I have to process the instruction is what? I fetch, right? I go and fetch the instruction. So let me put a line here. Anything that has to do with fetching, which is program counter, right? Anything that has to do with the program counter is in the fetch stage. Then anything that has to do with decoding is in the decode stage, right? I go to the decoder figure out, okay, these are the instructions, send out all the signal, right? And then I have to execute stage. What does the execute stage do? Basically do whatever the decoder tells you to do. Add, multiply, jump, or skip the execute stage and go to access the memory, right? In this case, we're gonna assume each of these stages take one cycle. For now, let's assume it take one cycle, right? Uh, Sorry, I've been talking for 2 hours, 20 minutes. My throat is. I was teaching the functional programming class earlier, so I need something to help. But yeah, so let's when you have to access the memory, let me call that a memory stage. And the last stage, we typically call it write back. Right? Anyone want to take a guess why we call this write back? That's when we store the results, right? So we would write everything to the target location. Usually these are destination, like destination register. So what is the task that have to do? You write it back to the register and you update PC, right? Don't forget to update the PC, right? So this is basically in the multi-cycle architecture. And this is how, let's, for the purpose of this class, this is how we will pipeline. This is a typical 5-stage pipeline. If you go to read a computer architecture textbook, this would be the classic way to pipeline because each of the stage exactly do its own thing. fetch, decode, execute, memory, and write back. And then one thing I have to tell you, in the real CPU, you actually slice this fetch into multiple stages, decode into multiple stages, execute into multiple stages, right? So you can slice this more, way more, into 30 to 40 stages so that you can clock it really fast. But from the fundamental point of view, this is the classic 5-stage pipeline. When everyone says 5-stage pipeline, think this diagram, all right? Because this might come up in the future when you read like computer architecture, someone refer to like a classic computer architecture pipelining, think this diagram. So what are the key issues here? Imagine, right? So imagine I have instruction 1 here, instruction 2 here, instruction 3 here, instruction 4 here. This is basically I have 5 batches of clothes, right? And I have to wash them, dry them, and fold them. First batch, second batch, third batch, fourth batch, fifth batch. How can I manage the control signal? So let me ask this. How can I manage the control signal? Something like, what address do I put it here? What should be the select line value over all over these places? Right? Think about it. These select line should be for instruction 4, right? Because basically you're trying to select this is value going to the register file, right? It should be for instruction 4. But this select line, it should be to select next PC so that you get the correct instruction 5, right? This address would be for instruction 3. The data showing up here is from which instruction? Or which instruction right now process things in the memory? Well, if you think about this point, instruction 2. If you think about this point, instruction 1, right? And what do we know about wires? Can I have 2 different pieces of data in one wire? Yeah, it can only hold one single value, right? So what does it mean? Oh, it means they have issues. As simple as that. We need some. What do we do? What do we do here? In programming, let's say we move back to the software, right? In the software world, what do? I need to hold 2 values. There are going to be a copy of something that I can use to store this data, right? I'm going to have to store them in the middle. It's a temporary process. Think of it as a temp variable that you put in the hardware, right? You store and hold all the value so that you get the right things at the right place. So I'm gonna go through the text part now that I draw things on a figure. So these are the key issues. Let's say each of the stage is handling different instructions. Instruction 1, instruction 2, instruction 3, instruction 4, instruction 5. It means that the design somehow have to process all the signal for all 5 instructions at the same time, right? Fetch is instruction n, decode n minus 1, execute n minus 2, memory n minus 3, and write back n minus 4. Anyone want to take a guess which one is the one that programmers see? Right now, so let's say I run the program. You actually don't see the execute. When will my register file get updated? Actually, not at fetch as well. Fetch is too fast. I haven't seen the updated version. Write back, right? This is the key. Write back is when the programmer see what's happening. Remember our microarchitectural state back in 2 lectures ago that I say whatever happened underneath, we're not telling the programmer. This is one example. You have pipelining going on. You only see this. You only see, oh, my register get updated. When that register get updated, you didn't even realize your computer actually take in already 4 more instructions, right? Why do you want to do that? Well, make things faster, right? Laundry example, it's gonna be a lot faster if you can do washing and drying at the same time. Why not, right? So this is where it becomes visible to the programmer. So it means that in this case, because they are visible at the write back stage, register files and the program counter is updated at write back, right? And other state has to store the intermediate value, which is not visible to the programmer, but we don't need to tell them. As long as they're correct, I don't care. These intermediate values. Oh, so by the way, are you all in agreement that first of all, you need intermediate values? Second of all, the programmer only see what happened after you finish write back. When you finish write back, programmer see, aha, that's my changes. All right. So these intermediate values that store things that programmer doesn't see is called pipeline register. Simple as that. What does register do? As we all know it, is store data, right? Store temp thing, right? Store any temporary data. So pipeline register, it doesn't store real like instruction data. Well, it does, but it is not visible to the programmer. I just put it there to make sure I can remember where I am in the pipeline. So I put in the right thing at the right time, right? So I can store multiple intermediate data. These intermediate value is being saved when it goes through each of the pipeline, right? And the pipeline register will store there'll be one for fetch, one for decode, one for execute, and one for memory. I mean, right back we use the architectural register. Architectural register is the one visible to the programmer. So once I update that, I'm good. I basically make it seen, right? So you need one for fetch, one for decode, one for execute, and one for memory. So what is that? This is good. We can implement pipelining, but what would be the downside? So cost. You need to add things. It's as simple as that. So the reason why I have this bullet point showing up is there's actually quite a lot of things you can do in hardware to make things faster. Everything is a trade-off. If you want performance, sometimes you have to pay the price. If you want performance, sometimes you have to pay the actual area on the chip. If I buy a processor, what does it come with? So ALU, caches, right? The cache comes with your CPU. So if I use more area on the chip for this pipeline register, it means that I will have less area for my cache, right? Because everything is about that big, same size. The package looks the same. Literally, you have the same area where you can put transistor on. If I use more for the register, you have to pay the price of using less for the cache. You have to pay the price of using less for the other logic to make your computer faster. So it's all about balancing the trade-off, right? How can we make it at the Pareto optimal at the right trade-off? So here, let's put in pipeline register. The way I would draw it is simple. Vertical black bar, red bar. Think of this as actual register that store data, right? That store data. So I have this instruction 5 address here, right? PC is pointing to the address of instruction 5. I'm going to store that in this red bar. Well, it basically, this one, the way I draw is a little bit wrong, to be honest. Why is that? Anyone want to point out why this part is a little bit wrong? Yes, that's a great question on the chat about Moore's law, right? Moore's law is about how many transistors we can cram in a unit of area, and it's double every certain amount of time. So does Moore's law mean that the compromise will be reduced in the future? Yes. The more transistor we can pack in, the more things we can put in on our chip, right? So that's why it's important. Well, that's why it's important that we can scale things down from say 15 nanometer to 10 nanometer to 7 nanometer to 5 nanometer. The smaller the transistor is, the more transistor you can pack in the same area, right? That's why scaling is really important. So over here, the fetch unit actually go directly to the memory so that we can get the instruction. But it will, it's gonna hold the instruction so that the decode instruction come here, right? It's for instruction. So let's say this is instruction 5, instruction 4, instruction 3, instruction 2, instruction 1. Instruction 1 is at the write back stage, right? Which instruction is in the decoder right now? Four. I just draw 4. 4 is in the decoder. So it means instruction coming in here is for instruction 4. Instruction 5 is waiting to be put in the decoder, right? So think about this way. This instruction come in here is for instruction 5. And we use the buffer right here, right? So basically instruction 5 is right here, waiting to be put in here. With me so far? And right now, instruction 3 is here, right? Instruction 3 is being added, it's being multiplied right now. So the data that comes out over here, this one belongs to instruction 3, right? I'm adding this. So the result of an add is specifically for instruction 3. With me so far? At the same time, the input that you see right here, also belong to instruction 3, right? Because the input for the add has to be belonging to instruction 3, right? Because we are in the execute stage, we are processing whatever is for instruction 3. But at this point, things that are being going right into the input in the next cycle, which instruction does it belong to? Okay, yes, sure. So there's a question about like, can I explain again? I will. And that's the correct answer. This is for instruction 4. So let me actually erase everything on the slides, right? And I wanted to say, hey, right now, write back is write back is for instruction 1, right? Then instruction 2 is in memory stage. Instruction 3 is in the execute stage. Instruction 4 is in decode stage. Instruction 5 in the fetch stage, right? Are you with me so far? So it means that if I look at instruction 1, right, instruction 1, this particular data, it belongs to which instruction? Instruction 1, right? Everything that are in this write back stage has to belong to instruction 1. Look at the same wire. So it means that this particular buffer has to store whose data? It's a buffer, right? So it stores temporary data. It right now it stores the instruction 1 data because it is basically it store and feed that data to everything who needs it, right? How about this buffer, is it for instruction 1? Is it for instruction 2? Is it for instruction 3? The one that are in the memory stage. Instruction 2, right? Let's say instruction 2 is, instruction 1 is add 5 and 10, right? So over here, data should be what value? Instruction will say, I want to add 5 and 10. So what's the value I should see right here? Is the result of the add, so you should see 15, right? Let's say instruction 2 is add 1 plus 2, right? If I look here, if I look at this line, what value should I see? 3, right? It should see the value 3 because I'm basically storing the value 3 that comes from my adder one cycle ago. But over here, I'm storing the result of my add 2 cycles ago, which is 15. All right. So are we all with me so far? Okay. How about this? If I look right here, and let's say this instructions multiply 3 and 10. If I look right there, what's the value I should see? Yes. So the question is it okay to just assume that the buffer register store the data for the upcoming stage? That's what it is. Right? So do you start to see now how can I put things together from a physical thing that I can basically build? I can build this buffer. I can build the wires, right? The copper wires. I can lay them out. I can drive the signal from one direction to another, right? The line for the ALU is the output. So what value should I see? 30. Yes. So you should see 30 right here because it's instruction 3, right? How about this? If I look at this, my bad. Let me erase. If I look at the input to my multiplier, which is right here, right? What should I see? I should see 3 and 10, right? Because I'm basically multiplying 3 and 10. So over here, the input should be 3 and 10. Source 1 and source 2 should be 3 and 10. Right? So over here, this buffer should store 2 things. Source 1 is 3. Source 2 is 10. Right? Your source before you multiply. And because it's a combinational logic, it means that once I feed in 3 and 10s, you will see 30 as the output in the same cycle. It's just and or gate. It's just a bunch of logic operations that are done in one cycle. So I put in 3 and 10, I should get 30 back. Right? Are you all with me so far? Any questions so far? Okay, let me refresh. Is this still confusing? Or can I go? The mux is it is in the decode part because we just need to store the result of my decoding, right? I just want to figure out, okay, what is the input to the ALU? So the mux will be before that. Why is the mux before that? So that I don't need a lot of buffer before the mux. Right? It's cheaper this way. I don't need as many buffer. Right? And anything in here will be for instruction 4. It will be for instruction 4. Wait, what is source 3 and source 4? Sorry, I was confused. There's a question of source 3 and source 4. So what do you mean by that? Oh, that's source 1 equal. Okay, sorry, my handwriting. Sorry. I'm writing source 1 equal 3 and source 2 equals 10. Okay, let me rewrite. Source 1 equal 3, source 2 equals 10. Basically, this is source 1 and this is source 2. This is the input to your multiply, basically. The input to the multiply. Input to the left and input to the right. One is 3, the other one is 10. We just need to make sure this particular buffer store the input specifically for instruction 3, not instruction 4, right? Same goal for everything inside the decode stage, right? The instruction here should be for instruction 4. Instruction 5 should be waiting for that buffer. And this is all, right? This is all, that's it, right? So unless you want to dive deeper to implement this real ship, this is it. This is how you can build pipelining, right? For now, right? So let me move forward. The next question is, well, how many pipeline stages do we need? You can add more, right? You can slice the memory into multiple stages. You can slice the ALU into multiple stages. And in fact, that it's done, right? Real ship do that. You can add more stage to allow faster clock. Basically, so that you can clock faster. You can have a 3 gigahertz clock and a 4 gigahertz clock rather than 1 gigahertz clock, right? It also enables more structure to be active at all time, so you get higher utilization. What would be the downside? Faster clock consume more power. You need more buffer, for sure. You need more buffer. Things are more complex, right? You need to make sure every instruction is at the right place at the right time. This one you have to trust me. But if you actually try to implement it in the real like hardware language, it's super annoying to get it right the first time. It's super annoying because you need to figure out, is this one coming from the fetch? Is this one coming from the ALU? Which one do I buffer? Do I buffer the right one or the wrong one? Because if you buffer just one wrong wires, your outcome is incorrect, right? So it's really, really fine-grained detail. So let's talk about how many cycles does it take. So let's say I have a program with 4 instructions, and a 5-stage pipeline, right? And let's assume every single stage is 1 cycle. We assume a magical world here, a magical world where every single stage take 1 cycle. First cycle, what do? Instruction 1 fetch, right? Washer and dryer again. I fetch the first instruction, right? Oh, so there's a question on why is the area on the CPU called the die area, right? It doesn't mean die as in you're dead, but it die means the logic die. It basically it's called that thing you see on the chip. That's why we call it die area, because it's actually the area on the die. Yeah, that's why we call it die area, essentially. Right. So, okay, let's resume. How many cycles does it take, right? So we can go through this one by one. The first cycle, instruction 1 goes into the pipeline, right? What happened in the second cycle? Which instruction get fetched? Which instruction get decoded? In the second cycle. Can I move instruction 1 to decode? Yes, right? So I can move this to decode, this is fetch. I'm not doing anything else, right? In the next cycle, I finish decoding instruction 1, so I'm going to execute. This one is being decoded. Instruction 3 is being fetched, right? Memory, execute, decode, fetch. Right back. Memory, execute, decode, done. Well, it's done since here, right? Right back, memory, execute, right back, memory, and right back. So how many instructions in total? I mean, sorry, how many cycles in total to finish these 4 instructions? 8, right? So we need 8 instructions. Again, sorry. We need 8 cycles to finish the 4 instructions. Let me change the example a little bit, right? So with the, okay, let's stick with the same example, right? We assume that there are 2 multipliers. It will still take 8 cycles, right? Why is that the case? If multiply take 1 cycle, in total it will take 8 cycles, right? Same thing, because the first multiply in the execute, the other multiply is in the decode. They can move on in the next cycle. But what if I say multiply now take 5 cycles? This is the same example as my drying machine is taking longer, right? Now multiply take longer. What would happen? So I'm gonna go move on to the table format, right? Now multiply take 5 cycles, right? So can I fetch? I can, right? Fetch decode, execute. How long do I need for the execute to finish? Multiply take 5 cycles, so how many? I'm gonna put execute here, right? Because it does take 5 cycles in this particular assumption. Instruction 2, when can I start fetching instruction 2? Definitely not a trick question. So cycle 2 you can fetch, right? And I can keep fighting with PowerPoint. Apparently, if I draw it far enough, it will let me write. And then cycle 3 I can decode, right? Can I execute at cycle 4? I have only 1 multiplier. So I can't do anything, right? Until cycle 8, right? I can decode here. I cannot execute until cycle 8 because I only have 1 multiplier. It's the same problem with my washing machine and dryer, right? I only have 1 dryer and they take long, so I have to wait. Cycle 8, I can go to memory and write back. Memory, oh no, execute again, right? 5 cycle. When can I fetch instruction 3? Yeah, you can throw money at the ALU. That's correct. So you can fetch in cycle number 3. When can I decode? Can I decode in cycle 4? What is stuck in decode? Yep, decode has to hold the value for instruction 2, right? So I can start decoding right here. And when can I execute? Cycle 13, right? Because I get stuck here too. Execute, memory, and write back, right? I can't even fetch until here, right? Because fetcher is still holding the instruction from instruction 3 until cycle number 8. Oh, actually, I forgot. Yes, XOR. Okay, thank you so much. It's XOR, not a multiply. So this takes 1 cycle. So let me redo that. I fetch an XOR instruction. I can decode here, right? Once I decode, I can execute here 1 cycle, memory, and write back, right? Fetch, decode, execute, memory, and write back. I forgot that multiply take 5 cycles, the rest take 1. Thank you so much for pointing it out. That's why it does fit in the table. For some reason I was like, this doesn't fit. That's weird. All right, thank you so much. Any questions about this? The reason why I need to erase is I somehow thought instruction 3 is a multiply. So it is an X4, it takes 1 cycle, the load also take 1 cycle. So that's instruction stall, right? You have to wait. You have to wait. So instruction stall basically means that, first of all, there cannot be enough resources to move the instruction. In this case, I don't have a buffer, or my multiply is too slow. I only have 1 multiply. Okay? So I cannot move the instruction through the pipeline. The effects, so what will be the effects here? That's a great question. So there's a question on the chat that says, can the ALU execute different instructions at the same time? You are talking about what CPU these days are doing. Yes, we have more logic to handle that. So they can run multiple instructions at the same time, right? But let's assume this really simple 5-stage pipeline with nothing else, no fancy tricks. Right now, the fact is things are slow, right? Things are slow. What can be the case? First of all, the other example that we just saw, not enough functional units. Sometimes some steps take longer. Sometimes you have unbalanced design, right? And what do you do to ensure the correct results? You make things wait. You make things wait, right? Everything slow down. With me so far about the downside of like, okay, if I have the things that are unbalanced, sometimes your instructions stall, right? And to be honest, instruction stall is the source of performance degradation in every single program. One way or another, if memory take a long time, you stall. If going to the hard drive take a long time, you stall. If your compute is not really, really well designed, you stall, right? So things slow down because of instruction stall. If you say want to add more resources, you can say we have what we call Superscalar Architecture. We are not going to go into too much detail, right? But the overall idea is in the Superscalar Architecture, we add more functional units. Can we add more multipliers? Right? Yes, as simple as that. The second instruction would do the multiply alongside the first one with 2 multipliers. Okay, with me so far? So this is called Superscalar Architecture. We are not gonna actually explain how to make sure everything is still correct because that's too much detail. That's for the next architecture class, not for this class. We don't have enough time for that. But this is one way you can fix it. And superscalar architecture is everywhere in the CPU world. It's everywhere, right? So we can add more fetch unit by fetching more instruction, right? Make the fetch unit fetch 4 instruction at the same time and make sure that we can issue them all, right? It's actually being done in the CPU that you buy. In the CPU you buy, you have a fetch unit capable of getting multiple instructions in a cycle. You can have more adders, more multipliers. You can have more a unit that can send memory access all at the same time. Anyone here heard about memory bandwidth? Memory bandwidth is important because modern day CPU issue the memory at the like multiple memory requests at the same time. We don't stall. We keep issuing. You say, hey, I want this address, I want that address, I want that address too. Right? So you're issuing multiple memory requests at the same time. This is called Superscalar Architecture. And one of the key things here is, well, if you want to put something in, make sure they are balanced. If your workload is just a bunch of floating point multiply, make sure you have a lot of floating point multiply and not a lot of, say, adder, right? It allows more instruction to be dispatched. Dispatch means I'm going to put instruction into the pipeline to run it, right? When I said dispatch, it means that I'm start running that instruction. So it allows you to dispatch more instruction per cycle. You can fetch more, you can decode more, you can execute more. And this exploit what we call instruction level parallelism. This is when you have a code that can run multiple instructions in parallel. If instruction 1 can go along with instruction 2 and instruction 3, it has higher instruction level parallelisms than a code that have instruction 1, you have to go there because instruction 1 produce results for instruction 2. Right? So we'll go into that in a bit. These are the cause of instruction stall. If you have, well, you all have taken system seal class, right? So I hope. You might have realized one thing I'm preaching is accessing data takes a long time. Going to the main memory takes a long time. This is one of the main cause of instruction stall. So this is what's slowing down your program. Another thing is what we call branch misprediction. I'm gonna explain it in a bit, right? With this diagram. So let's say this is a branch instruction inside the execute stage, right? I'm jumping somewhere. Basically, this is like if something, do this, else do something else, right? Do I know what instruction do I fetch here? So let's say this line is instruction 10, and this line is instruction 100. And I'm trying to figure out the result of an if else. What is my next line? Now you have a choice, right? Between instruction 10 and instruction 100. Are you all with me? Basically, right now, I'm trying to figure out, do I take the if or do I take the else? So it means that I don't know what is my next instruction. So I don't know what would be in my decode. I also don't know what would be in my fetch. Right? With me so far? Any questions here? Because in the execute stage, I'm trying to figure out inside that if else clause, is that true or false? And because of that, I'm basically I basically don't know what should I fetch next, right? So if you're with me so far, what do I do here? So feel free to keep typing because everything I've seen so far, well, take both is one correct thing to do. Well, not sure because if you let it crash, it means your program crash, right? So the obvious thing to do is what do? We wait until we know, right? Take a gamble is another great thing to do. Everything here is correct. Yeah. So I'm gonna cover that in the future lecture. This is called branch prediction. So what are the answers so far? One option is take both, right? Take both is a legit answer. This technique is called dual path execution. I don't know what I'm gonna take. I'm gonna fetch both of them and somehow execute both of them. Once I know the result, I'll throw away one branch. I'll throw away one side, right? Why can't I throw it away? That, okay, when I said I can throw it away, you can do both and then use mux later to pick the correct one. Yes. But the reason why I can throw it away is, does a programmer ever see what I'm doing? No, right? Because it doesn't reach the write back yet. So the programmer doesn't see it. In secret, I'm taking both branches. That's why dual path execution can work. You run both paths. Uh, guess is a real thing, right? So every single CPU that you have, every single CPU that you have in the world do this. They guess if it's going into the if or if that's going to the else. There are uh, there's like a huge body of research on how to do that guess. Right? In fact, my I guess great grand advisor, like my advisor, the advisor of my advisor is one of the world expert on how to do that guess. He is working on branch prediction. His name is Yale Pat, and he's one of the really, really big name in architecture. Uh, Guessing is the correct answer. You can guess. And again, if you guess wrong, what do you do? So if you guess correctly, awesome, right? But if you guess incorrectly, what do you do? If incorrect, throw it away, right? Because you haven't put that in the right back. So programmer doesn't see it. Well, yes, guess again, but there are only two options. If the first option is wrong, the next time you guess, you're gonna get it correctly, right? Yeah, you go into another option, right? If you guess I'm going to the if, oh wrong. So let me go to the else, right? So this is the concept of branch prediction. This is called branch prediction. So this is basically what can happen and what can slow things down, right? You have branch, you have if else. Yep, you can. It cause instruction stop if you guess incorrectly. All right, with me so far. The next thing that slows things down is called data hazard. Right? So what the heck is data hazard? Let me go through this example. What is about this colored text that I have? What is the relationship? And let's assume this is destination, source 1, and source 2. Basically, the first line, I'm going to multiply R1 and R2, write the result to R0. What's the problem here? It is a chain, right? It used the data produced by previous instruction. It used the data produced by previous instruction. What does it mean? When can I know the result of the previous instruction? After write back, right? Well, by default, after write back. If you are being really aggressive, when? So internally, after execute, right? After I finish the execute stage, I know the results. So if I want to cheat, I can just go there and peek at the result at the execute stage too, right? But at the end of the day, these can stall things, right? So in this case, let's assume you have one multiplier and multiply take 5 cycles. Memory access take 50, right? So it means that before this part and this part, I have to wait 5 cycles. I have to wait 5 cycles before I know what is R0. So this will take 5 cycles. Over here, also another 5 cycles, right? Until I would know what is the result of R3. And then over here, 50 cycle. Now you start to see why load and store is a pain. Because if you have dependency, which is really common, you go get something in your array and you want to add one, right? You need to get that array data to add one. It takes 50 cycles, right? So this is called data dependency, right? Data dependency. So with this pipelining, the number of cycles it takes to execute this, I'm gonna just to draw this fetch, decode, execute, right? So you can fetch, oops, decode. What is not letting me draw things? Oh my god. Okay, I can't draw. Fetch again, not. Oh, right. Fetch. Don't fight me. Fetch, 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 fetch. You all know it's fetch. Okay. Decode, execute. How many cycle? Multiply take 5, right? So it takes 5 cycle. And then memory and write back, right? So you can fetch here, decode here. When I can execute, I'm sorry, when can I execute? With the data dependency, I have to wait until I know R0. I know R0 right here, right? So I can execute. Memory, write back, right? I need R3, so I can basically, so you can fetch here, you can decode here, you can execute right here because that's when I know R3. R3 is here, R0 is here. Execute, memory, write back. You can fetch here, you can, when you have to hold the decode, right? Oops. Because you have to hold the decode, so the decode here happens right here. And you have to hold the decode again up to here, so you can decode, execute, memory, write back. The problem here is memory take a long time, right? Instruction 4 is a load. Instruction 4 is a load. So this is gonna take 50 cycles. All right, so data dependency on data hazard cause instruction stall, okay? So let me classify different types of data hazard so that, let's come back to this, right? The dependency here generates data hazard and is a really, really common in every single program. And there are ways you can actually kind of address it, right? So there are multiple types of data hazard. The one that you've seen, true dependency or read after write. What does it mean? I need that data after I'm producing it. I'm producing the data and then I need to read it. The other two types of data hazard will not show up in the architecture we learned in this class. What we learned in this class is called in order architecture. What does it mean? You execute every instruction in the order that you've seen. Instruction 1, followed by instruction 2, followed by instruction 3, followed by instruction 4, followed by instruction 5. In modern day CPU, what we do is we call it out of order execution. Basically, the idea is if I can run instruction 10, because I have the data ready, I'm gonna issue them. If I can, so basically at the end of the day, the CPU might be running instruction 1, then instruction 10, then instruction 2, 3, 4, and then instruction 11, instruction 15, followed by 5, 6, 7, any order, right? As long as the programmer see the same order at the write back stage, you're fine. This is called out of order execution. So with out of order execution, there are two more data hazards that can show up. Right after read. Right after read means that I fetch the future instruction. It reads it writes something, right? It writes something. The future instruction writes something. It's supposed to happen after a read, so there's a dependency there. There's also right after write. This again can happen in out of order. You have instruction 1, do a write. Instruction 10, do a write. But you somehow schedule instruction 10 before 1, so you write instruction 10, then you write instruction 1, which is a wrong order. So you need to make sure you preserve that. So in an in order pipeline, in an order in nope. This for the next class. You don't have that assignment. Let me get rid of it. You don't have that assignment. In an in order pipeline, only read after write exists. Only read after write exists. So how do we deal with data hazard, right? How do we deal with data hazard? The obvious way is we wait. We wait until we have the data. We wait until we have the data. We wait until the data is in the write back stage. The programmer see the result, fine, we can go. We are waiting in the decode. The decode is going to wait until the write back finish. In case of raw data hazard, we need to make sure the operands take the correct value. So our pipeline register is gonna send out empty instruction, doing nothing, basically doing nothing until that earlier instruction is in the write back. Downside is gonna be slow, right? This is safe because I'm gonna wait until I know the data in the write back, right? Once we're in the write back, for sure, that's the correct result, so I can resume. Can we do better? So when is the earliest that I'm gonna know the result of an add or multiply? Even if it's an add or multiply, after execute, I know it, right? And if it's a memory instruction like load, if it's a load, when do I know the result? In the memory stage, right? In the memory stage, I will know what's my data. So we can take a peek at those data and use it as my operand. This is called data forwarding. Right, this is called data forwarding. So I'm gonna take care of each of these designs one at a time. The first design that I'm gonna show is I'm gonna put in bubble. Right? So let's say instruction 1 over here is to add 0 plus R1 and produce R2, right? Instruction in the execute stage is I'm gonna add R0 and R1, produce R2. Instruction 2 is basically I'm gonna add R2 plus R3, produce R4. With me so far with this particular example? Okay. If I want to insert the bubble, the next cycle, which now I'm gonna use a green color, right? Instruction 1, move here. Instruction 2, do nothing. It stay in decode. Insert bubble here. Bubble means I'm not doing anything. Don't do anything. I'm waiting. I'm waiting in decode. This is next cycle, right? In the next cycle afterward, I'm going to use a different color, the orange color, next cycle again, right? Instruction 1, move to write back. It hasn't finished the write back yet, right? It hasn't finished the write back yet, so I don't have the data. I'm going to put in bubble here as well. And this bubble move here. So I'm not doing anything for 2 cycles now. I'm waiting in decode. Then I'm gonna use, okay, I'm running out of color, blue, right? So I'm moving to the next cycle. This is done, yay, right? Bubble move here. the second bubble move here. Because I'm done, instruction 2 can now move here because now I know what is R2. Okay. With me so far? Basically, these allow me to make sure I have my data, okay, inserting this bubble. And every time I insert a bubble, it means that I'm going to slow things down because I'm not computing anything. And here is how can I tell when do I stall, right? It's called stall condition. You stall when the instruction that you're running need the value produced by previous instructions that are still in the pipeline. Emphasis on still in the pipeline, right? Instruction is still in the pipeline, you have to stall, right? And the distance of the stall determine how long you have to stall. So let's say it's next to each other. You stall for that long, right? 3 cycles long in the earlier example. If the instruction that are creating dependency is in write back, then I wait 1 cycle because 1 cycle I'm finishing the write back, I have my data. So that's 1 cycle. You must stall until the data is fully written back to the register file. Until the data is fully written back to the register file. So here is the if else, huge if else block. It's an if block basically. If this is true, you stall. ID is decode. ID comes from instruction. In decode, source requires some instruction that are inside execute, memory write back. You stall. And if the source ID is matching, basically if say you need R2 for your source, right? If you need R2 and someone is producing R2, you stall. If you need R2 and someone is not producing R2, you don't have to stall. This is basically a block that you can put in the hardware design that say stall when this is true, right? So this is basically a logic state that describe what I explained in the earlier slides. If the next instruction depends on some of the instruction in the pipeline, wait until they're written back, then you can resume. All right. So here is the analysis. Right, here's the analysis. You can have register, right? R1, R0, something that produce something to register, a load, store, branch, or jump, right? Or jump based on register. In the decode, typically, you can sometimes need to read to the register, right? So this is the condition. I need to know what's the value of my register. When do I produce the result? That's in the write back, right? R type will produce the register value. Load will also produce a register value. Your instructions are safe to resume whenever this finish. Again, encapsulate what I described earlier. You block in decode until whatever is blocking you is finishing the write back. Wait until the dependent register finish the write back state. That's all. That's the key. Basically, let them finish the write back. So this is a conservative solution. Wait, the next thing is called data forwarding. Data forwarding is, hey, let's be aggressive here. As I said, if I have ALU operation, when's the earliest I know the result? Right. I can't spell. After execute, right? If it's memory, this right after memory. So I know the results internally. So data forwarding is based on that observation. I know the result once I'm done with execute. So do we need to wait for the write back? Do we need to wait for the write back? Yes or no? Not really, right? You don't have to wait for the write back. The idea is, the reason why it's called data forwarding is to forward the results that are still in the pipeline to the future instruction that are still waiting for that result. So for each instruction, you look at the source register. If any instruction in the pipeline finish computing that source register, forward the data whenever that becomes available. So this is going to solve read after write dependency, right? It's going to solve read after write dependency because it will make you stall a lot less. You can stall a lot less, right? Data forwarding is basically something like this. Over here, you know the result of your computation, right? Let's say that's the data dependency. So instruction 2, instruction 1. This produce 0, need 0. So let's say instruction 1 produce 0, instruction 2 need 0. Over here, this is 0, right? I'm basically have the data, right? I have the data right after my ALU. So what can I do? Instead of getting R0 from here, right? Instead of getting R0 from here, this is the old R0, which is wrong. It still has the wrong value. You forward it into your mux and you select that line. You make sure the mux select this new R0. So let's say instead of instruction 1 produce R0, instruction 1 has nothing to do with R0, but instruction 0 here produce R0, right? So when do I have that data and where is that in the design? So when instruction 2 is in decode, right? When instruction 2 is in decode, R0 is here, right? In that wires, because you still have that data, right? From instruction 0. So you can forward it here and you select this wire. So basically that's the key behind data forwarding, right? You forward the data whenever that becomes available. So let's do some analysis again, right? By looking at this table, fetch, decode, execute, memory, and write back based on instruction type. Execute, produce the instruction, right? Memory can also produce instruction, and then the rest use the register. So if you look at this diagram, what's the only one case where the pipeline still have to stall? There's only one case here when you have to stall. And that's when there's a gap between, yes, exactly. There's an answer on the chat that say load, right? Let's be more precise. Load after load. Because the first load doesn't know the data until what? Until memory, right? Things like back-to-back load will stall the pipeline. So this sounds nice. You get rid of most data dependency, right? You get rid of most data dependency. Anything that follow a load is the only case that can cause data dependency because execute is before the load. So you need to stall one cycle. Things like back to back and then the first instruction is a load can cause data stall. Anything that has to do with a load and you have the data dependency in the next instruction. So produce to here, 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 or here, and sometime to here. The only time you have to stall. So what's the trade-off? It seems nice, right? So the trade-off is for the benefit, you have fewer number of stall cycle, mean high performance. It's complex and consume more power again, take more area out of your chip. Considering in a real chip, sometimes you have 30 stages and you have to forward them all. This can be annoying. You have to forward the data everywhere, right? And we haven't really talked about branches as well. We'll come back to that. Right now, that's it for today's lecture. We cover pipelining and we cover data forwarding, right? There's an in-class exercise on Canvas that I would like you all to go through. So I'm gonna join the Discord in a bit. Before we leave today, I want to make sure you all aware Project 3 is out. I will delay that by one day. I'm sorry. There was something kind of emergency that happening, so I need to delay everything by a day. To context switch and go through all this like things that came up. So I'm gonna release it tomorrow. It's almost done. I just need to double check that I have everything listed out and no bugs on my starter code. All right. So it's gonna be released tomorrow. And then right now is the time to do in-class exercise. It's our second in-class exercise, but it's called activity for lecture 20. I think this is lecture 20. So please go there, take a quick look at that. I'm gonna switch over to Discord in a bit, all right? Okay, cool. So see you all in a bit. Let me just stop the recording, save the lecture slides, and then I'll switch over to Discord.